All right, I'm going to finish up the talk by discussing future directions for this work. I'll briefly show where you can find my work on the topic, but since this is a YouTube video, you can pause that at will, and I'm going to focus on where next. So one thing is, well, I've computed the entropy and index of the Angenent torus, but there are more self-shrinkers, and you can compute the entropy and index of those. One thing that makes the Angenent torus a good starting point is that it's rotationally symmetric, but there's sort of a gentle way to wean ourselves off of the rotational symmetry, and that is to take two rotationally symmetric self-shrinkers, for example, take the sphere and the Angenent torus, and take their union. That is, well, it's not a smooth surface because it has self-intersection, but it is an appropriately defined, it is still a self-shrinker. And one thing you can do is you can actually take this surface with self-intersections and desingularize it. So the idea is you have your sphere and it intersects the torus, and you can cut out that intersection and glue in something else that will make an embedded surface that is embedded and also a self-shrinker. So you can see these papers for how to do that. And so that's certainly a very good starting point for taking our ability to compute the entropy and index of rotationally symmetric self-shrinkers and moving it to a setting where these desingularized surfaces are no longer rotationally symmetric, but they should be very computable, and we should be able to find their entropy and index. There's also been work on self-shrinkers with birotational symmetry. So this is another setting where you can reduce to a one-dimensional case, again making things easier, but there are sort of a wider variety of examples there to try to compute entropy and index for. Another future direction is to use elastic flow to compute self-shrinkers more effectively. So let me talk a little bit about how that helps. So the idea is that if I have a surface, say it's golf ball shaped, so almost a sphere but with some dimples, and let's say I know that there's a self-shrinker nearby. Of course that's the sphere, but let's say I don't know what the exact self-shrinker is, I just know that there is one nearby. Well, then I can run mean curvature flow, and that golf ball will become rounder, and I will asymptotically find the self-shrinker that I'm near. And as we saw, that's not true for the Angenent torus. So the Angenent torus is an unstable critical point. So if I start nearby and I know that there's a self-shrinker nearby, just by running mean curvature flow, I'm not going to find it. Generically, I will miss that critical point. So the nice thing about elastic flow is that that these self-shrinkers are still critical points for elastic flow, but they're also minimizers, so they're stable critical points. And so this idea that I described of starting with something that's close to a self-shrinker and then running a flow to asymptotically approach that self-shrinker doesn't work if we run mean curvature flow, or technically speaking rescaled mean curvature flow, but it does work if we run elastic flow. And so there's some success there in the rotationally symmetric case, but one would like to extend that to be able to find and compute more self-shrinkers. And of course, one thing I alluded to earlier in the talk is that these numerical experiments are all well and good, but as mathematicians we want to prove things. And so what we would like to do is to prove, to have bounds on the accuracy of the entropy values and also on the eigenvalues that I computed in the index computation. So I counted the number of negative eigenvalues to be sure that I did that those results are accurate. I need to know that the error in those negative eigenvalues is small enough that they're not secretly positive eigenvalues that only look negative due to the error. And so there's some starting points in those directions as well. So there's certainly theorems in numerical analysis about how fast your discrete approximation, so maybe piecewise linear surfaces or whatever you want, how they converge to how fast they converge to the true things. So we have a little bit more complications here, right? So this work that I'm citing is in Euclidean space, but we have a weight, and also uh, we want a little more refined analysis. We want not just convergence rates, but we want to have actual bounds. But fundamentally, it's the same techniques. Fundamentally, all of these are boiled down to Taylor's theorem, and Taylor's theorem does give us bounds of how close our approximations are to the real thing in terms of some derivatives of certain quantities, which we should be able to compute and bound explicitly. Alrighty, so I'd like to thank you for your attention, and I'd like to thank Hoju Lee for organizing this workshop. Thank you.